Okay, we've already seen the conservation of mechanical energy, and so this is really sort of a repeat of what we saw before, and that is that energy is conserved in a closed system. What's going to be different here is that we're just want to define what an open system and a closed system are, what that refers to. When I say if a system is open or closed, it's referring to the energy or work that's being transferred into the system. So in an open system, energy or work can be transferred into the system. So you can think of an open system like an open box. All right, and then work and energy can come into it, work and energy can go out of it, and so the total amount of work and energy within that open system is open to change. A closed system, on the other hand, no energy or work enters or leaves the system. And so here we can think of a closed box, and whatever energy or work I have in this box, no matter the whatever the energy is, that's what it's going to be. So that system will always have the same amount of energy. So in a closed system, the total energy remains the same for all time. So in a closed system, the change in energy is equal to zero. Now, if a system is not closed, we can enlarge the system to include other parts so that the total energy does not change. So let's say that I'm looking at a person, and the temperature of that person just keeps going up and up and up and up. And we don't really know why. It's like the total energy of that person is increasing because their temperature is increasing. They're increasing in thermal energy, but we don't know why. Well, if we make the system a little bit bigger, we might learn that that person is standing next to a fire. If they're standing next to a fire, the thermal energy from that fire is heating up the person and making them warmer and warmer. So if I look at the person and just this as my system, well, that's an open system, and there's work or energy coming into that system and actually causing the total amount of energy of that system, which is the person, to increase. On the other hand, I can make that system bigger so that it includes not just the person, but also the fire. And then I have a total change in energy that's equal to zero because there's no other energy coming to or leaving the system. Now, let me give you another example. A moving bicycle is not a closed system. A moving bicycle is an open system. Kinetic energy appears and causes the bike to move. So if I have this bicycle, let's see, can Chad draw a bicycle? Uh, I think I'm drawing that backwards. Okay, there's my moving bicycle. It's just moving around. There's nobody on it. However, if you include the person who's actually riding the bicycle, then that becomes a closed system. Because, you know, the source of that energy on the bike was the person. So if I have this person that's on the bike, if I include him or her in that system, then that's going to be a closed system. I can expand my system so that it goes from being open to closed by including all the sources of energy that are in that system. So the energy is converted from the man's muscles in this case. And then those, of course, gain energy from the food we eat. All is well in the world. It's a closed system. The total amount of energy within that system, which includes both the man and the bike, will remain the same. The energy in the man might decrease as he expends calories or food energy as he makes the bike move, but as his energy decreases, the energy of the bike increases. And so the conservation of energy holds. The universe is a closed system from a physical perspective, that there is no new energy coming into the universe. The only energy that is in the universe is just going between one form to another. So if you make your system big enough, eventually it would include all of the physical known universe, and that would be a closed system in this idea. Okay, so that's open and closed systems and the conservation of energy. Let's go ahead and do power. It's short here. Power is just the rate at which work is done. So remember when we talk about rate, it's always a time rate. And so the power is going to be equal to the work over time. Or we can think of power as energy over time. Remember, work causes a change in energy, and so often we'll use those interchangeably. The units for work are going to be a joule per second. That's the unit of energy or work uh, per unit time. I'm sorry, did I say the units for work? The units for power are a joule per second. And uh, let's see, what is the unit? Gosh, what is that? Right. The unit for power is the watt. Now, watt is the name of a person, W-A-T-T. And so when we capitalize it, when we abbreviate it, we capitalize that. Okay, let's pause there and then we'll come back with efficiency. Actually, no, let's continue on. We'll go on and do efficiency. It's a short section. So efficiency describes how much energy is converted in a particular task. Efficiency, I'm just going to define it here, is the power out divided by the power in. Remember, I put my little bases on my P's there, times 100%. That is the definition of efficiency. We can also express this in terms of work. And it's really going to be the same equation. I'll show you that the work output divided by the energy that is input well, times 100% is equal to our efficiency. That is our efficiency. Let me just show you that these are the same. We can look at the units. Power is joules per second divided by joules per second. That cancels out, and that gives me efficiency. There are no units for efficiency, by the way. But I just want you to notice that these seconds cancel and leave me joules over joules, which is what I have here, joules over joules here. Okay, let's imagine that I have a system that is 20%, I have a system and I put in 100 joules. But I get out 20 joules. Okay, so what has happened there is I've lost some of the energy. So what is the efficiency? I say 20 joules divided by 100 joules times 100% gives me a 20% efficiency. So whatever the system was, I have a 20% efficiency. So let's say that it is an engine. An engine might have an efficiency of about 20%. I think that's actually pretty close for a lot of engines. That I put in this chemical energy in the form of fuel, gasoline or diesel or whatever it is, and then I get out some amount of physical work, a force acting over a displacement. However, the amount of energy that I put in is a lot more than the amount of energy that I get out. And so where does a lot of that lost energy go? And the lost energy in this case, I'm losing 100 minus 20. I'm losing 80 joules of work. So we could say actually that this engine is 80% inefficient, that it's actually losing 80% of its total energy. Well, most of that energy is going to go into heat, and I'll show you an example in class where we have a conversion from kinetic energy into thermal energy. In fact, many engines lose most of their energy to thermal energy, which is generally thought to be lost. It heats up the surrounding environment, and then that energy is not really usable anymore. So when I say that energy is lost, it doesn't mean that it just disappears into thin air. It just means that it's not really usable anymore, and thermal energy is often not usable. Okay,